How much space to leave free on HDD or SSD? In the informal, i.e. journalistic, technology press, and in online technology blogs and discussion forums, one commonly encounters anecdotal advice to leave some amount of space free on hard disk drives or solid-state drives. Various reasons for this are given, or sometimes no reason at all. As such, these claims, while perhaps reasonable in practice, have a mythical air about them. For instance, once your disks are 80% full, you should consider them full, and you should immediately be either deleting things or upgrading. If they hit 90% full, you should consider your own personal pants to be on actual fire, and react with an appropriate amount of immediacy to remedy that. Source: to keep the garbage collection going at peak efficiency, traditional advice is aimed to keep 20 to 30% of your drive empty. Source: I've been told I should leave about 20% free on a HD for better performance, that a HD really slows down when it's close to full. Source: you should leave room for the swap files and temporary files. I currently leave 33% free and am vowed to not get below 10 GB free HDD space. Source: I would say typically 15%, however with how large hard drives are nowadays, as long as you have enough for your temp files and swap file, technically you are safe. Source: I would recommend 10% plus on Windows because defrag won't run if there is not about that much free on the drive when you run it. Source: you generally want to leave about 10% free to avoid fragmentation. Source: if your drive is consistently more than 75 or 80% full, upgrading to a larger SSD is worth considering. Source: has there been any research, preferably published in a peer-reviewed journal, into either the percentage or absolute amount of free space required by specific combinations of operating systems, file system, and storage technology, for example magnetic platter versus solid state? Ideally, such research would also explain the reason to not exceed the specific amount of used space, for example in order to prevent the system running out of swap space, or to avoid performance loss. If you know of any such research, I would be grateful if you could answer with a link to it plus a short summary of the findings. Thanks.
Has there been any research, preferably published in a peer-reviewed journal? One has to go back a lot further than 20 years, of system administration or otherwise, for this. This was a hot topic, at least in the world of personal computer and workstation operating systems, over 30 years ago, the time when the BSD people were developing the Berkeley Fast File System and Microsoft and IBM were developing the high-performance file system. The literature on both by its creators discusses the ways that these file systems were organized so that the block allocation policy yielded better performance by trying to make consecutive file blocks contiguous. You can find discussions of this, and of the fact that the amount and location of free space left to allocate blocks affects block placement and thus performance, in the contemporary articles on the subject. It should be fairly obvious, for example, from the description of the block allocation algorithm of the Berkeley FFS that, if there is no free space in the current and secondary cylinder group and the algorithm thus reaches the fourth level fallback, apply an exhaustive search to all cylinder groups, performance of allocating disk blocks will suffer as also will fragmentation of the file, and hence read performance. It is these and similar analyzers, these being far from the only file system designs that aim to improve on the layout policies of the file system designs of the time, that the received wisdom of the past 30 years is built upon. For example, the dictum in the original paper that FFS volumes be kept less than 90% full, lest performance suffer, which was based upon experiments made by the creators, can be found uncritically repeated even in books on Unix file systems published this century. For example, Pate 2003 p. 216. Few people question this, although Amir H. Majidama actually did the century before, saying that Z has in practice not observed a noticeable effect, not least because of the customary Unix mechanism that reserves that final 10% for superuser use, meaning that a 90% full disk is effectively 100% full for non-superusers anyway. Majidama 1996 p. 68. So did Bill Calkins, who suggests that in practice one can fill up to 99%, with 21st century disk sizes, before observing the performance effects of low free space because even 1% of modern size disks is enough to have lots of unfragmented free space still to play with. Calkins 2002 p. 450. This latter is an example of how received wisdom can become wrong. There are other examples of this. Just as the SCSI and ATA worlds of logical block addressing and zoned bit recording rather threw out of the window all of the careful calculations of rotational latency in the BSD file system design, so the physical mechanics of SSDs rather throw out of the window the free space received wisdom that applies to Winchester disks. With SSDs, the amount of free space on the device as a whole, i.e., across all volumes on the disk and in between them, has an effect both upon performance and upon lifetime. And the very basis for the idea that a file needs to be stored in blocks with contiguous logical block addresses is undercut by the fact that SSDs do not have platters to rotate and heads to seek. The rules change again. With SSDs, the recommended minimum amount of free space is actually more than the traditional 10% that comes from experiments with Winchester disks and Berkeley FFS 33 years ago. Anand Lalshimpi gives 25%, for example. This difference is compounded by the fact that this has to be free space across the entire device, whereas the 10% figure is within each single FFS volume, and thus is affected by whether one's partitioning program knows to trim all of the space that is not allocated to a valid disk volume by the partition table. It is also compounded by complexities such as trim where file system drivers that can trim free space within disk volumes, and the fact that SSD manufacturers themselves also already allocate varying degrees of reserved space that is not even visible out with the device, i.e., to the host, for various uses such as garbage collection and wear leveling. Bibliography. Marshall K. McCusick, William N. Joy, Samuel J. Leffler, and Robert S. Fabry, 1984-08. A Fast File System for Unix. Acme Transactions on Computer Systems. Volume 2 Issue 3. pp.181-197. Archived at cornell.edu. Ray Duncan, 1989-09. Design Goals and Implementation of the New High Performance File System. Microsoft Systems Journal. Volume 4 Issue 5. Pages 1-13. Archived at wisconsin.edu. Marshall Kirk McCusick, Keith Bostick, Michael J. Kerrells, and John S. Quarterman, the 30th of April 1996. The Berkeley Fast File System. The Design and Implementation of the 4.4 BSD Operating System. Addison Wesley Professional. ISBN 2015499794. Dan Bridges, 1996-05. Inside the High Performance File System, Part 4, Fragmentation, Disk Space Bitmaps and Code Pages. Significant Bits. Archived at Electronic Developer Magazine for us/2. Keith A. Smith and Margot Seltzer, 1996. A Comparison of FFS Disk Allocation Policies. Proceedings of the Usenix Annual Technical Conference. Steve D. Pate, 2003. Performance Analysis of the FFS. Unix File Systems, Evolution, Design, and Implementation. John Wiley Amp, Sons. is the 9,780,471,456,759. Amir H. Majidama, 1996. Optimizing Unix for Performance. Prentice Hall, is the 9,780,131,115,514. Bill Calkins, 2002. Managing File Systems. Inside Solaris 9. K Publishing, is the 9,780,735,711,013. Anand Lalshampi, the 4th of October 2012. Exploring the relationship between spare area and performance consistency in modern SSDs. Anantech. Henry Cook, Jonathan Ellithorpe, Laura Keyes, and Andrew Waterman, 2010. IOTFs, Exploring File System Optimizations for SSDs. IEEE Transactions on Consumer Electronics. Archived at stanford.edu. This URL. Exceligao, the 10th of April 2017. A summary on SSD and FTR. GitHub.io. Does Windows trim unpartitioned, unformatted, space on an SSD?
Though I can't talk about research being published by peer-reviewed journals, and I wouldn't want to have to rely on those for day-to-day work, I can though talk about the realities of hundreds of production servers under a variety of OCs over many years. There are 3 reasons why a full disk reduces performance. Free space starvation. Think of temp files, updates, etc. File system degradation. Most file systems suffer in their ability to optimally lay out files if not enough room is present. Hardware-level degradation. SSDs and SMR disks without enough free space will show decreased throughput and, even worse, increased latency, sometimes by many orders of magnitude. The first point is trivial, especially since no sane production system would ever use swap space in dynamically expanding and shrinking files. The second point differs highly between file systems and workload. For a Windows system with mixed workload, a 70% threshold turns out to be quite usable. For a Linux X4 file system with few but big files, for example video broadcast systems, this might go up to 90+%. The third point is hardware and firmware dependent, but especially SSDs with a SandForce controller can fall back in free block erasure on high write workloads, leading to write latencies going up by thousands of %. We usually leave 25% free on the partition level, then observe a fill rate of below 80%. Recommendations. I realized that I mentioned how to make sure a max fill rate is enforced. Some random thoughts, none of them peer review, paid, faked or real, but all of them from production systems. Use file system boundaries. /var doesn't belong into the root file system. Monitoring. Use a ready-made solution if it fits you, else pass the output of DFH and let alarm bells go off in case. This can save you from 30 kernels on a root S with automatic upgrades installed and running without the auto-remove option. Weigh the potential disruption of a F's overflow against the cost of making it bigger in the first place. If you are not on an embedded device, you might just double those 4 grams for root.
Has there been any research into either the percentage or absolute amount of free space required by specific combinations of operating systems, file system, and storage technology? In 20 years of system administration, I've never encountered research detailing the free space requirements of various configurations. I suspect this is because computers are so variously configured it would be difficult to do, because of the sheer number of possible system configurations. To determine how much free space a system requires, one must account for two variables. The minimum space required to prevent unwanted behavior, which itself may have a fluid definition. Note that it's unhelpful to define required free space by this definition alone, as that's the equivalent of saying it's safe to drive 80 miles per hour toward a brick wall, until the very point at which you collide with it. The rate at which storage is consumed, which dictates an additional variable amount of space be reserved, lest the system degrade before the admin has time to react. The specific combination of OS, file systems, underlying storage architecture, along with application behavior, virtual memory configuration, etc. creates quite the challenge to one wishing to provide definitive free space requirements. That's why there are so many nuggets of advice out there. You'll notice that many of them make a recommendation around a specific configuration. For example, if you have an SSD that's subject to performance issues, when nearing capacity, stay above 20% free space. Because there is no simple answer to this question, the correct approach to identify your system's minimum free space requirement is to consider the various generic recommendations in light of your system's specific configuration, then set a threshold, monitor it, and be willing to adjust it as necessary. Or you could just keep at least 20% free space. Unless of course you have a 42 TB RAID 6 volume backed by a combination of SSDs and traditional hard disks and a pre-allocated swap file. That's a joke for the serious folks.
Of course, a drive itself, HDD or SSD alike, couldn't care less about how many percents of it are in use, apart from SSDs being able to erase their free space for you beforehand. Read performance will be exactly the same, and write performance may be somewhat worse on SSD. Anyway, write performance is not that important on a nearly full drive, since there's no space to write anything. Your OS, file system and applications on the other hand will expect you to have free space available at all times. 20 years ago it was typical for an application to check how much space you had on the drive before trying to save your files there. Today, applications create temporary files without asking your permission, and typically crash or behave erratically when they fail to do so. File systems have a similar expectation. For example, NTFS reserves a big chunk of your disk for MFT, but still shows you this space is free. When you fill your NTFS disk above 80% of its capacity, you get MFT fragmentation, which has a very real impact on performance. Furthermore, having free space does indeed help against fragmentation of regular files. File systems tend to avoid file fragmentation by finding the right place for each file depending on its size. On a near-fill disk they'll have fewer options, so they'll have to make poorer choices. On Windows, you're also expected to have enough disk space for the swap file, which can grow when necessary. If it can't, you should expect your apps getting forcibly closed. Having very little swap space can indeed worsen the performance. Even if your swap has fixed size, running completely out of system disk space can crash your system or make it unbootable, Windows and Linux alike, because the OS will expect to be able to write to disk during booting. So yes, hitting 90% of disk usage should make you consider your paints being on fire. Not once have I seen computers which failed to boot properly until recent downloads were removed to give the OS a little disk space.